So the next thing is introducing the orthogonal expansion or orthonormal. Usually we'll do orthonormal, but sometimes the bases are not normalized. Like the Fourier series, usually we use sine and cosine, which are not normalized, which is fine as long as you carry the normalization constant around. That's fine. That's basically by convention and by tradition. So because we have the uh, scalar product, how do you define the scalar product? So we define the basis function, a set of basis function for psi. So you have the psi of phi. These are we call the basis function of a given vector space. So I can be finite. I mean, it can be, it can start from any number, or it can be just stop at any final number, or it can go to infinity. It doesn't matter. So it depends on what the vector space. We have a finite number of bases, and you use these bases to define your vector space, or any linear combination of these bases becomes the order function in your vector space. And that is fine too. And we define the condition for orthogonal is so the phi I and phi j is 0. I not equals to j, then they are orthogonal, right? And then because scalar product usually is, I mean, it's by definition greater or equal to 0, and the equals here only for the function is identically 0. So usually you can normalize that if you have a set of bases satisfy this orthogonal condition. So you can just require phi I is equals to 1, and then it becomes a orthogonal. Or if it is originally it's not defined, obviously you can make it orthogonal by divided by this scalar product with itself, or the square root of the scalar product with itself. That you make it orthogonal, or make it orthonormal. So make it normalized. So combining these two, and orthonormal set with this scalar product with itself. By Kronecker delta. Okay, so that's straightforward. And so once we define the basis of any function, f can be expressed as a linear combination of these bases. In the textbook's notation, it's a sub I, so sum of I, a sub I, and I, phi I, not j. Okay, and again, it can be sum over a finite number of them or infinite number of them. If for infinite number of bases, obviously, then you need to have some convergence condition. You make sure this converge this sum, and that extra condition for that. Usually just assume they can until you found a expansion that is not converging. Okay. So once you have that, then this expansion, and you can use the orthonormal condition to find the a sub I, just like what we did with Fourier series. We first write as expansion of sine and cosine, and then we pick out the coefficient for this expansion by using integration, and which is in our case, is the scalar product. Okay, so so what we can do is do a scalar product F with one of these spaces. Define my F, the scalar product. It's just then you just substitute this in here by I. And somewhere here to here, then when you put it in here, you don't use the same I. This is a dummy summation, dummy index for the summation. So you change that to J. Is J, and J, right? And you take out all the coefficient. So that is sum of J is J by I, which is the Kronecker delta. But this is just the Kronecker delta. Sum over J, meaning this will give you answer. Okay, so just it's just like what we did for the Fourier expansion. We did that before. But once we have that, we can now substitute this back to here and write like sum over I. Now this is this I is just this one. So I, okay, so that's the orthonormal expansions like that. Okay, so that you've seen this before in your series. So because we have done that, we don't need to look at the example because the example is just the Fourier series. We've seen that. The next example is an example with this. The scalar product not defined by integral, but it's defined by just definition. This is some basis for spin that in quantum mechanics. And you could do that. And that thing is it's just basically a definition. You can do expansion like that. You don't necessarily need the scalar product to be defined by integral. As long as you define the product, that you can still do expansion like that. And yeah. This one? Well, this is a scalar product of F with one of these functions, phi. This is just the usual definition of scalar product. So I'm saying that the scalar product doesn't have to be defined by an integral. You can just define whatever, how you define your scalar product with this, your basis. That you can just maybe just define it by hand, and that would be fine too. Just like in that example, the spin example. Right. So that is fine. That just means that the function space describing this thing is not defined by a function of variable. And that would be fine too. Okay, that's what you're asking for. Okay, and now once you expand the function, say your alpha defined by that, you can now do your scalar product using this coefficient. Then you just basically represent the function using your set of coefficients and use that to do calculation like scalar product. Say if you have defined like that, I see the text use B, G is sum over all the set of B sub I, the coefficient for the G function is this set of B. Then you can do the scalar product as F and G. Just substitute all this, substitute this into here, this into here. It becomes sum over I, plus I, sum over J, J. Right, and following the same way. So So you take out all the constants, it becomes just the scalar product of phi sub I, phi sub j, because all these a sub I, these sub j's are just numbers. They're just constant. You can take that out of the scalar product. And the scalar product of I and G are this conical delta. And so that you can use the conical delta to do one of the sum. You have two sums, sum over I, sum over J. So sum over J using the conical delta basically is changing all the J to I. So that the sum of I and the A sub I, and that's going to be A sub J. And the reason our complex conjugate is because it's on the left side, right? Because of the coefficient on the left side becomes a complex conjugate. Okay. That is the scalar product of a function in terms of the expansion coefficient. Once you expand the function in a certain basis, then you do a calculation on the coefficient. It's just like a vector when we are expressing vector into component of like a coordinate system, and you have the component of along different unit vectors. So those becomes a number to represent that vector. And once you define the coordinate system or the calculation, you can just use those numbers, use the coordinate to do calculation. And just like that, you expand, choose your basis, then you expand everything in the spaces, then you get this, all this coefficient basically like the coordinate. You can use this coordinate to do your calculation like a scalar product or a vector is a dot product, right? Once you do that, the base expansion, you can forget about your basis and work with all these numbers, right? And then the good thing about this is once you have done all this definition or calculation of the scalar product of the basis and normalize that, then all this calculation doesn't involve integration anymore. It's just sum over the product of these coefficients. You forget about all the how you define it, whether by integration or not. It doesn't matter. It's just like linear algebra becomes a change the or original problem that might involve integration. Now it just becomes a work out the linear algebra. Okay, so that's that make it easy. So that's one of the motivation why it goes through all this trouble to define basis of the vector space. And because once you do that once, then the rest is just linear algebra. Okay. Yeah. All right. So a special case, of course, it's the scalar product of function itself. Just use this definition with some complex conjugate I, which is just sum of I, the compact magnitude square. Right? Then that's straightforward. Right. Another way to look at that, this one, you can, if you treat f, so this, if you expand this f, create f, and treat it like this is like a column vector. So all this a sub I form a column vector. And when you put that on the left-hand side, becomes a row vector. So this is, you can write it like a row vector A1, A2, A3, and so on. This is a vector. But when you put it on the left-hand side, you remember to do the complex conjugate. And the original one, you treat it like a column vector. Right. Then this product is just like this multiplication of a row vector with a column vector. that exactly like that. So that's why it's like linear algebra. Once you define the basis, this all this product, even this is like a row vector of F multiplied by a column vector G, which you get this one. And there's a name for that. And if you like to write it as a vector form, so this is called the or matrix form. This is called the complex conjugate transpose of Hermitian. What we call that? We use this dagger notation for that. Is the the adjoint of the original vector. This is if you want to treat it like a vector. This is the adjoint vector. It's basically a complex transpose of the vector multiplied by the vector. So a column vector, the transpose becomes a row vector. The row vector multiplied by a column vector. And take the complex conjugate of the row vector. Okay, so all these are just notation. The next example is also trivial. Is again the Fourier expansion. So we've done this before, so you can skip that. All right. So the next topic is this Bessel inequality, which is quite straightforward. It just means that if you do an expansion like that, and you're not sure that this is a complete expansion or not, and then the Bessel inequality say that this you can do a scalar product like this one, the scalar product. Bessel inequality saying the scalar product of the function itself, just by whatever you define a scalar product like integral. And this would be greater equals to this expansion square, which is in our case this one. Right. So if it is complete, then you have the equal sign. But if it's not complete, this expansion is not complete, then this one will be greater than that. If it equals, this is what you have seen before in Fourier series. This is called the Percival identity, where if the equal sign is a Percival identity. And the greater sign is when this is not complete. Fourier series is complete, so it's equal sign. But if you define just a limited number of your bases, not include all the bases, then the expansion is not complete, and you get this one. And to show that is do that minus this expansion, whatever that is. The expansion is this one. So which is this the ace of I. Just do it more explicitly, right? And then find I, and then that's F. Yes. That is by definition of scalar product is greater than zero. Right? Then you work out this product. That will go to this scalar product F and F, and then this and that, so minus J, and then F by J. Right, and then this and that. I right. Oh, but when you do it again, when you do expansion when this is the coefficient on the left, so you need to take the complex conjugate. Right? And this and that is this. And then finally is this and that is plus sum of I, sum of j, and this one again, complex conjugate. And this one. Phi I phi j, which is delta j. And then you identify that this one you can exchange the order of the scalar product and take the complex conjugate. This is the same as this is just the definition of scalar product. You see that all three terms are actually the same because now you have the Kronecker delta. You can sum over j. Just forget about the j summation. Change. Oh, I actually it's the same. Just change that to I. I and J's are the same. These are just dummy variable. So all three terms will be the same, right? And just basically, you can cancel one of these. You know, cancel one of these with this. With this and minus that is greater than 0, and this is just this summation, right? Right. So that's just show that this Bessel identity, Bessel inequality. How you show that is valid. Okay, yeah.
Yes. First, graph F, and here closing it. So, okay, the second line.
This one?
Yeah.
Yeah.
So you find you have the graph F before the first one. No, let me show you. So here.
Yeah.
Yeah. Closing it.
No, this is you have four terms. You have two terms on each slot, right? You just distribute this scalar product. The first is this scalar product, the first term and the first term. So F and F is this one. This one is this one with this one. Is this one. The third one is this one with this one, right? The last one is this one with this one. Okay, altogether you have four terms. All right. And it's just to show that there's a cancellation. And once you have the cancellation, you get the Bessel inequality. Is that okay? Yeah. All right, so all these are pretty straightforward. And then the next example is saying that you can use the expansion, this basis expansion for even function that has that is discontinuous, which we have seen in our Fourier series expansion. Also, we expand this step function or all that. You can do that, although subject to the convergency problem near the boundary. But as long as you sum all of them, then they finally converge to a discontinuous function. Right. So it can be done, and so this even if that you have this equality, doesn't exactly means that this expansion is exactly like F. So this expansion sometimes will involve a discontinuity, or so it's not uniformly converged. So it's not every point is converged. It's just integral because this F, this scalar product involved in integral. Just integrating the scalar product itself is equals to this sum. So sometimes you can allow the existence of isolated discontinuity. Okay, so that we have seen even in Fourier expansion. All right, the next one is you have always did that in the Fourier expansion. Is just another way to look at this completeness condition. Basically, now instead of this arbitrary f, you just expand your delta function. Right? Right? You can just use that. Just use this one and that one, right? So that have to be a delta function. The textbook should say delta function x minus t naught. Again, string notation one is like we usually associate t with time x is space, but anyway, that's the way the text is written. So, so you use the same expansion, the sum of I, about the function. Right. And now this delta function, if this is just like a integration, right? Just the usual integration definition. See, this coefficient, like if it's defined like if I write if this is just like a usual definition is phi I equals delta x minus t, right? And dx. That's this is this scalar product. And then phi I. Now phi I is a function, you can see. And in this definition, you don't have to wait, but that just the simple case of that. If you are weight, then the completeness will carry the weight function also. But if there's no weight function, this integration is just trivial. It's just changing the whatever the argument of the function, change it to t. Okay, so that is summing whatever the number of bases you have, or infinite number of bases. You recover the delta function this way, and I usually call this a completeness condition, but there's another name. It's called the closure. Talk about that. Anyways, I guess the meaning is the same. You close the system in all these spaces. All these spaces form a complete set. If they form a complete set, they need to satisfy this condition. Right. All right. So that is the complete this condition, and we again we've seen that like we use the Fourier series to do this completeness condition. And all right, so okay, all this notation is, I guess, these spaces, property of these spaces are like that. And one more remark is that we make this discussion on discrete basis. We assume you have a discrete number of bases. I is maybe even infinite many of them, but they still are discrete. One, you can count them like 0, 1, 2. But sometimes we are using bases that are continuous, just like what we did now. Just take the limit of Fourier series to the continuum limit, and we define the Fourier transform. And now the Fourier transform is like you're expanding a function using a continuous basis. So now this phi, instead of index I, you have phi because another function, like in that case, is the wave number k or something like that. You depend on another continuum variable, and then this expansion instead of a summation becomes integration of these bases. So if this depends on k, the wave number, this becomes a sum integrating over k. And this coefficient, again, are given by the scalar product of this continuum basis of the original function, just like what we did in the Fourier transform. And as it turns out, for the Fourier transform, the special case is that the form of this integral for defining the basis, the calculating coefficient, and the expansion is similar. It's just reversing the k and x, right? And yeah, so that another way to do the expansion, but with a continuous basis, you just basically change all these discrete basis with a continuum. One thing is that this of a normal condition in continuum becomes a little bit problematic. It's instead of delta, conical delta actually becomes because of both depends on k, right? But then the different I and j means a different k, and this summation is just what you define is as becomes a delta function become k, like one is k, the other is k prime, the delta function k minus k prime. So an example is you've seen that in Fourier transform to 1 to 2 pi dx. You think just one dimension, right? You have really the I. It's this that k minus, right? The orthogonal condition, like for the continuum basis, the right hand side becomes a delta function instead of conical delta. Okay, so that's a remark. And likewise, now this orthogonal continuous condition also involve an integral instead of sum, right? So, but the general extension for discrete spaces, the continuum basis are quite straightforward. You just follow the rule, and then you can do exactly the same thing. All right. Okay, up to here. Any question up to here? All right. So the next topic, I think I talked about that before, and some of you have seen that in quantum mechanics, the Dirac notation. All right. So it's just another way to write all these things. I probably mentioned that before, but do it more systematically. So instead of writing a function, so in this notation, the bases are given by a function, right? Just write like a phi I, without any extra notation. But in Dirac notation, this basis can be just like you write like what we call the cat vector, right? And later on we'll define a Bragg vector just like that. So this orthogonal condition is just the scalar product between a cat vector and Bragg vector. Altogether is bracket, so they call it Bragg vector and cat vector. So so this is so cat vector is this is Bragg cat vector and Bragg vector like that. So this is like putting this together, and although supposedly you have two straight lines, right? But when you put it together, you just simplify it to just one straight line and share this within the Bragg vector and cat vector. And likewise, this is still true. I mean, in Dirac notation, you can do it like that. And now the function, any function in the vector space also, you can expand the cat function, the cat vector of that function like that. So instead of expanding with phi I, you use all these cat bases, right? And then here, right? And all these are fine, all these are fine. So the only thing different is that like delta function or actually any f, we're going to continue with this one. So this f continue with this one, but reverse the order of this thing. So because this is just a number, you can write this this vector multiplied by that number, just reverse the order. cat vector basis. And this coefficient, right? That's nothing but why this constant after the vector, which is allowed, right? And the trick here is now you separate this line out, and then write like a sum of I, and I. Right. So as if this is a separate object multiplied by f, and then and this actually have the same form as this one, because now if you write in Dirac notation, this is the cat vector, right? And this is the vector because it has a compact function. This becomes a vector too, right? But you reverse the order of that. Reverse the order. Right? So this is the delta function, but delta function x and t, and so and so it has the similar. So basically, you this becomes this one, but you're actually calling this not the delta function. In this case, it's like f becomes something multiplied by f itself, and you can say this is just one, or more precisely, because this is a vector, it's not, it's just one. It's like an identity matrix. This becomes identity matrix multiplied by the vector itself. So, but usually in quantum mechanics, people just call it one. Right? Or this closure relation, this becomes this in Dirac notation becomes sum over this object becomes one, right? And you can, if you go back to this column vector and row vector, and you know that this is this cat vector becomes a column vector, right? This becomes a row vector. A column vector multiplied by a row vector becomes a matrix, right? So we have column vector whatever number of a's multiplied by okay, actually the other way around. This is column. Like that kind of a notation is just like that, writing a product of a column vector and a row vector. And this kind of matrix multiplication actually results in a matrix, right? So this becomes you know the matrix multiplication, right? So A from A, the first one is A1, B1, B2, and so on, right? This actually is a matrix. You treat it like that, and in this case, because both are the same basis function, and that becomes identity matrix, right? And so you can do that, and the Dirac notation is a little bit of abuse of notation because this is a tricky. This is originally just a number, and then you separate it out into this object. It's a little the language is a little confusing. But anyway, it is convenient, and many people doing quantum mechanics like to do that because you just whatever says like app originally app, you just insert that multiplied by one, then you get the expansion right away without going through all these scalar products, right? And now you get the expansion formula just like that. This becomes convenient to do things, but the more rigorous way derive this expansion formulas is what we did before. Okay. All right. I guess that's the end of chapter section 1. Okay.